Hi everyone, this is the Green Team's video on central processing units. Today we will go over how the CPU interacts with memory and how the CPU executes programs. To start off, we're going to do an overview of the central processing unit subsystems. First, we have the program counter, which carries the address of the next instruction. Next, we have the L1 cache memory. This is known as fast access memory. This is because the CPU can execute instructions much faster than they can be fetched. Because of this, it's more efficient to fetch several instructions at once and then storing it in the L1 cache so the CPU has fast access to them. Next, we have the instruction register, also known as the current instruction register. This holds the instructions that's currently being executed. Next, we have the control unit. Once the instructions have been fetched and are ready to be decoded, the program counter will update its address to the next address of instructions, and the current instruction register will send its instruction to the control unit to be decoded. The instructions are in the form of bit patterns stored in memory. They come in the form of electricity passing through transistors. The electricity passing through, or ons and offs, can be represented as 0 off or 1 on. Zeros and ones make up the language of binary, which is the language of computers. This process helps decode the instructions sent from the current instruction register. Once the instruction has been decoded, we can start thinking about the logic of that instruction. This is where the arithmetic logic unit comes in. This performs arithmetic and logic on instructions. Here we have a brief example. Here you might get something like an adder circuit, such as a full adder. A full adder is a combinational logic device that has 3 1-bit inputs, carry, X, and Y, and 2 outputs, which would look something like this. Depending on the configuration of transistors, that will determine what type of logic gate you're dealing with. Next, we have the registers, which is a named group of memory within the CPU. Data from memory is organized in CPU as registers. In the CPU status registers, we have what is known as the current program status register, the application program status register, and the save program status register. The current program status register, or the CPSR, provides information about the current executing program, both at an application level and at a system level. The application program status register, or the APSR, provides a view of the CPSR that is restricted to the parts that are accessible at an application level. The save program status register, or the SPSR, saves copies of the state of the CPSR when an exception occurs. There are 7, one for each execution mode. Now we can see how CPU interacts with memory. As an example of how data can be stored in memory, let us imagine that we have some data in one of the CPU registers. Storing this data in memory is affected by setting the states of a group of bits in memory to match those in the CPU register. The control unit can be programmed to do this by, number 1, placing the memory address on the address bus, number 2, placing a copy of the register bit state on the data bus, and then, number 3, placing a write signal on the control bus. For example, if the 8 bits of memory at this address are in this state, and the R0 register of the CPU is in this state, and the control unit is programmed to store 1 byte from R0 at this location, the control unit then, 1, places this address on the address bus, places this address on the data bus, and then places write signal on the control bus. This causes the bits at this memory location to be changed to this state. Now that we've done the overview for the CPU, let's put it all together to see how the instruction execution plays out. First, a sequence of instructions is stored in memory. Second, the memory address where the first instruction is located is copied to the program counter. Third, the CPU sends the address in the program counter to memory via the address bus. 4. Memory responds by sending a copy of the state of the bits at that memory location on the data bus, which the CPU then copies into the instruction register. 5. The instruction pointer is automatically incremented to contain the address of the next instruction in memory. 6. The CPU executes the instruction in the instruction register. 7. Go back to step 3 until there are no more instructions to execute. Hope you enjoyed our video, and thanks for watching.